I highly recommend you play with this simulation. So this is a simulation where you have, two planets orbiting, and you can change the masses of either one of them, and you get to see where the center masses are. It's kind of fun. So please, it says binary stars. Okay, so there's two stars, not two planets, whatever. So I hope you will take the time to play around with that. Okay, so this equation is just for the x center of mass. Well, what if we have something in 2 dimensions? Well, not a big deal, right? Then here's our x equation. Our y equation is the same. You just put y instead of x. Whoopee! Okay? So, I'd like you to do this, please. So figure out the x center of gravity and the y. By the way, center of mass and center of gravity, same thing. So figure out the x and the y. But hold it. Before you do the work, just think for a minute. So this is just the x, right? So all you're thinking about is x. So here you see 100. And here, what do you see? At the same x, you see 500, right? So see 100 here, 500 here. So where's the balance point going to be? It's going to be somewhere close to this, right? For looking at the y's, here you see 400 at y equals 0. And then up here you see 200. So where's the center of mass going to be? It's going to be somewhere down here, right? Okay, so figure this out. Let me give you the answers, though. So let's see. The x, center of gravity, or center of mass, is 8.33 centimeters. And the y, center of gravity, is 3.33 centimeters. Okay, just what we said, right? The x is over here. The y is over here. So figure that out. Make sure you understand it. And by the way, what's awesome about these problems, you don't have to convert units. I mean, as far as the, okay, so the answers are in centimeters, right? But what I'm saying, you don't have to convert the masses. Because look, you have a mass here in grams. You have masses here in grams. So there's no reason to convert the kilograms like we would usually do, right? Just leave it as it is. You can leave the x's in centimeters, and the answer will be in centimeters. That's okay. So these are really nice. Okay, here's a question for you. You've seen this before. I don't know if you've seen it before. A 1 kilogram rock is supported by a massless string from one end of a meter stick. What's the mass of the meter stick if it's balanced by a support at the 0.25 meter mark? Think about the center of gravity at the meter stick. So stop the video, pause the video, think. This is not easy. So think about it and then start up again. All right, let's talk about it. I assume you figured it out, hopefully. So look, the center of gravity is the spot where it acts as if all of the mass were located there. Okay, so this is a uniform meter stick. So the center of gravity is right here. So that means we're pretending that the mass of the meter stick is right here. Now I don't care about the string, that's irrelevant, okay? So we have this mass here, and then we have the mass of the meter stick right here. This distance here is the same as this distance, right? So if it's balanced, we have this mass has to equal this mass, right? Because if this mass equals this mass, then the force of gravity here equals the force of gravity here, the weight. We have the same lever arm, right? So the torques will cancel. So that's me. You don't even have to do any math, right? If this is a kilogram, then the meter stick is a kilogram because we're thinking of the mass of the meter stick right here at the center of mass. So we have a kilogram here, lever arm 1/4 of a meter, kilogram here, lever arm 1/4 of a meter. Okay. All right. New subject. Rotational inertia. All right? We had linear inertia. We didn't call it linear inertia. We just called it inertia. But it was linear inertia. Now we want rotational inertia. All right. So look at this. Just look at everything drawn here, all the vectors. Is this uniform circular motion or non-uniform circular motion? Hopefully, as soon as you look at it, you'll see a force here, and an acceleration here, and that means it's not that means that the speed is changing. So it's non-uniform circular motion. Again, this T, the centripetal force, changes the direction. This changes the speed. All right. We've got to do a little playing around with equations, okay? Okay, so that tangential force, Ft equals MAT, right? No kidding! Newton's second law, F equals ma, right? So that's not a big surprise. Now, what did we learn earlier? Earlier we learned S equals R theta, V equals R omega, A equals R alpha. And if you want to put little t's there, you can. You don't really have to. All right, let's substitute. Let's substitute for A sub t. So we have M R alpha. Okay, that's cool. I mean, yeah, that's cool. All right, so M R alpha. Okay, now, instead of using linear things like forces, let's use rotational variables like torque. It kind of makes sense, right? So what's the equation for torque? Well, torque equals F perp R. Well, okay, sorry. We can say F R perp, or we can say F perp R, whatever. So let's say F perp R, F perp. Now what is F perp? It's just Ft, right? Let's just put Ft. Okay, that's cool. Now, let's use this in here. Let's just substitute. All right, so Ft, let's put a T. So Ft is mR alpha. Then we have another R, so we have mR squared alpha, right? Or if we, I don't care, write it however you want. Right? M alpha R squared, whatever you like. Okay, we're going to use that. That's why we're doing this. Okay, so, oh my gosh. Now look, this is a blob, and each point here is a molecule. So there's gazillions of molecules, right? I'm just showing you 3 of them. So what we want to calculate is the total torque for every single molecule. Oh my gosh. All right? All right, let's just do it, right? Just be brave. So the net torque, just use that equation, yeah? So M1 alpha R1 squared plus M2 alpha R2.
Aloha. The meter service counter is now closed. The computer lab will close in 15 minutes. The circulation desk will close in 20 minutes. All receptor items allowed you. Mahalo.
Plus M3 alpha R3 squared, on and on and on. Now, how come I didn't have to put a subscript on the alpha? Because it's the same, right? Remember that ladybug, gentleman bug question? It's similar, right? Alpha is the same for every particle, you know? Okay, so that means I can make this look a little nicer, don't you think? So I can write the sum of mi Ri squared times alpha. All right, so that's pretty cool. All right, so the torque equals this mass times alpha. Now, Newton's second law of motion, what is it? F equals ma. So Newton's second law of motion, F equals ma, right? Now, what is the rotational equivalent of force? It's torque. What is the rotational equivalent of A? It's alpha. All right, so come on. Torque equals mass times alpha. What has to be the rotational equivalent of m? It has to be this sum, I call it a mass, right? So the equivalent of mass is the sum of mi Ri squared. So there you go. So this is the rotational version of Newton's second law. Now, you have to admit, this is a total disaster. That's not just kidding, but it's way more complicated than F equals ma. Because this thing here, not only does it depend on the mass, but it depends on where the mass is located relative to the axis of rotation. So it's way more complicated. But don't worry, it's not going to be bad. You'll see. Oh, sorry, forgot. Now, you don't want to write this all the time. It's too much trouble, right? So you write this thing here as uppercase I. And it's called the rotational inertia. So basically, this is what we have. So we have F equals ma. Then we have torque equals I alpha. So force becomes torque, m becomes I, a becomes alpha. Now the only problem is they should have thought of a Greek thing for I, right? I mean, they blew it. Oh well, such is life. Okay, so this is the rotational version of F equals ma. Torque equals I alpha. All right, let's go through this. M, mass. Mass is the measure of inertia. Inertia is the natural tendency of an object to remain at rest or at constant velocity. No kidding. If I have a piece of tissue paper here, it doesn't have much mass, it's easy to change its velocity. If I have a lead brick, it has a lot of mass, it's hard to change its velocity. All right, let's do the rotational equivalent. I, which is this sum, right? I is the measure of rotational inertia. Rotational inertia is the natural tendency of an object to remain at rest or at a constant angular velocity. So see how similar it is? It's completely related, you know? Completely related. Okay, so I'm just repeating myself over and over and over again. F equals ma. A equals F over m. A force causes a linear acceleration. Torque equals I alpha. So therefore, alpha equals torque over I. A torque causes an angular acceleration. Completely equivalent. So if you understand the linear motion in dynamics, this is free. You know, it's a piece of cake. All right. So here, let's do this. So if the mass is located at large R, what's I going to be? Well, large, right? If this is big, big number, this is going to be big, you know. I is going to be large. Thus, if you have a large I, and you have an ordinary alpha, what kind of torque are you going to need to rotate this silly thing? A large torque. Okay? That's all there is to it. All right, so this is my daughter-in-law and two of my grandsons. This is a long time ago. They have 4 kids now. So and this is a carbon wheel for a road bike. So which one is going to be easiest to rotate? This gigantic thing in a mine or this super light, tiny little carbon wheel? It's pretty obvious, right? Here, there's this doesn't weigh hardly anything. It's like less than a half a kilogram, right? So the mass is located far from the axis, but not too far. But the mass is almost nothing, so it's going to have a small I. So it's going to be easy to spin this thing. Here, oh my gosh, right? You have lots of mass located far from the axis. So it's going to be incredibly difficult to rotate that thing. Yeah, like I said, this is less than half a kilogram. This is like 5,400 kilograms. Just the tire, not the wheel, just the tire. Half a kilogram is the whole thing here. Okay, that's kind of cool. Okay, our last topic. We want to talk about rolling motion. Rolling motion. All right. Oh, I forgot to show you this, sorry. Okay, in the homework problems, you're going to be figuring out rotational inertias and torques and all that stuff. Well, this formula is a mess, right? I equals a sum mr squared. That's a mess. Well, luckily, for some common objects, here's the answers, okay? So if you want to find the rotational inertia about a rod about the center, there it is, right? 1/12 ml squared. Now here, look. Here, more mass is located further away than here, right? So this is going to have a larger I than here, which it does. This is a 12th, this is a third. Same thing here, right? This is going to have a larger, this is going to be harder to rotate than this. This is going to have a larger I than this because it's further away from the axis. So a 12th and a third, and so forth and so on. So you'll have this in your book, and you'll have this on your exam. And like I say, whenever you need to calculate I for one of these objects, there it is. So it's not so bad. Okay, last topic, rolling motion. This is kind of cool. You'll like it. So, okay, so when we say rolling motion, we mean no slipping. So I don't know why I chose this picture, because it's really wrong, because, you know, those guys, the pioneers, they had to go through a lot of mud, so they did a lot of slipping, right? So when I talk about rolling motion, it's this, no slipping. This is what I mean by slipping, right? That's slipping, right? That's not what we're talking about. We're talking about rolling motion. Okay. So here we go. So let's review some things. So let's say I do this. So I'm going to call that 100% translational motion, right? There wasn't any angular motion. That's called just translational motion, right? Now how about this? So that's purely rotational motion, right? There's no translational motion. The wheel's not getting anywhere. It's just rotating. Okay? So what is rolling motion? So rolling motion is both. So we have translational motion and we have rotational motion. Okay? So rolling motion is both. It's both translational motion and rotational motion. So here, this is an equation, huh? So pure translation plus pure rotation equals rolling, all right? So that's what it is. So that's one of these, you know, the picture's worth 1,000 words kinds of things. Rolling is pure translation, pure rotation. Simple as that. Okay, it's actually not so simple. All right. Oh, you didn't see that, right? Okay. Now notice here, you know, the v is to the right. Okay, here, you know, it's going like this, so the velocity is this way, here, that way, here, that way, here, that way. So here's the question. For rolling motion, what's the velocity here? And just to remind you, I mean instantaneous velocity. What is it? So just use this picture. Figure it out. So pause your video, figure it out. Okay, we're back. So look, here, that way, here, that way. These are the same magnitude, opposite direction. So what's the velocity? What's the instantaneous velocity there? Well, it's 0. What are you, crazy, brother? I don't believe that at all. Well, come on now. If I'm walking across the floor, what's my instantaneous velocity? When my foot, my shoe, sandal, whatever, touches the carpet, what's the instantaneous velocity? It's 0. If it were not 0, what would I do? I'm not going to demonstrate it. What would I do? I'd slip, right? I'd fall. Okay, you still don't believe me. Okay, look. Here's a wheel rolling. What do you see? You can see the spokes there. How come you can see the spokes there? Because because the velocity is 0. Here's a better one. What do you see? It doesn't look like it's moving, is it? Does it? Because it's not. Right? The instantaneous velocity at the bottom is 0. All right? What is the velocity? What's the instantaneous velocity up here? Pause the video and figure it out. Okay, we're back. Just do the simple math. You have a v to the right, same v to the right. That's going to be 2v to the right. Right? You don't, right? There it is. 2, right? V equals r omega, V equals r omega. This is twice, so it's 2r omega. Again, you don't believe me? Look at the pictures. Here you can see the spoke. Here, forget it, because it's moving 2v. It's going so fast you can't see it. Look at the next one. Can't see it, right? Here, doesn't look like it's moving at all. Here, wow, can't see anything. It's going so fast. All right? So that's kind of cool. How is this related to that? Just look. Same thing, right? Same thing. Okay? So V center of gravity equals VT. Okay? All right, and again, no slipping means we can use this formula, right? You know, V equals R omega. That means no slipping whatsoever. All right, let's just review. So we describe rotating motions in terms of angle, angular velocity, and acceleration. This is theta, omega, alpha. Same definitions as we've learned before, you know, except angular variables. So if you know the linear motion kinematic equations, you can figure out the angular, just switching the symbols, you know. We know how to compute torque. We'll do more next chapter, but we're still learning how to do it this chapter. Center of gravity, balance point, all of the mass acts as if it were located there, undergoes perfectly parabolic motion. Moment of inertia, this horrible thing here, right, which acts like the mass in F equals ma. Solve problems involving rotation and rolling. And I should have said one more thing here, right? Okay, F equals ma. The equivalent is torque equals I alpha. Again, I is this horrible thing. But again, I mean, I keep saying I is horrible. You know, you have that table, and most of the problems you'll use that table. So it's not so bad. Okay, thank you very much.